Hello guys, welcome to the fourth video of the series Algorithms in JavaScript. So in today's video, we'll be learning about graphs, right? Graphs are a really popular data structure, so which is highly used in the software world by programmers, different folks, different coders, you can say, to solve different types of algorithmic problems, right? So this is a really popular data structure, which is graphs, and even you would say the application of graph data structure is really important. It's really popular. It is highly used. Like if you can see in the day-to-day apps, in like Facebook, Instagram, different social media apps, the application of graph is humongous, right? So it is a really popular and really important data structure. Right. So, for solving problems which is related to graphs, so there are two types of very important algorithms involved, which are highly used by folks, right? So these two algorithms are, if you can see, depth for search and breadth for search, right? So these two are algorithms, in short, are called DFS and BFS. So why do we call them DFS and BFS? We'll learn about it later in the video, but for now, let's just remember that DFS means depth for search. Depth first or for search. BFS means breadth for slash first search, right? And I would say these are also the traversal techniques, because there is a graph in any data structure. What is the first thing you would do, right? In any data structure, what is the first thing you would do, right? You want to traverse that data structure, whether it is an array, whether it is a linked list, whether it is a string. You should have a way to traverse that data structure, right? So it is very important to traverse that data structure, right? So that is why we have these two algorithms, right? We have these two techniques, you can say, which is depth for search and breadth for search. So let's first try to get an understanding of a basic understanding of what a basic graph is, what actually the graph is, and how it is visualized, how it is represented, and then we'll move to the actual techniques, which are DFS and BFS, right? So okay. So, what is a graph, right? So I told you, like, a graph is a very popular data structure, but how it is represented actually? So graph is represented by these, right? So this is a graph, right? A connected set of items, right? A connected set of items. So every component like this, these are called vertex, or in multiple vertices are called vertices, right? And the boundary, or you can say the bridge between two vertices or two vertices, right, is called an edge, right? So this is an edge, this is a vertex. These two vertices has an edge, right? So every a graph consists of multiple vertices, multiple nodes. These are also called nodes, and they are all connected by edges, right? Okay, now that we know that, okay, you might have heard about binary tree also, right? A binary tree is also a graph, right? A binary tree is also a graph, right? This is also a graph. Okay, so there are different types of graph, mainly two types of graph, yeah. So undirected and directed, as you can see by the name, undirected and directed. So what is undirected? Which is no direction, right? So this graph, if you can name this vertices A and B, and it has an edge. Okay, now this is an undirected graph, means there is a relation between A and B, and there is a direction between B and A. You can go from A and B, and you can also go from B and A. You cannot differentiate between them, right? Unless they are not uniquely named. But there are two directions, right? This is two-way. This is not one way. You can, okay. Now, there is a directed graph, right? So directed graph have directions, one-way directions, right? You can go from A to B. A has a relation to B, right? Or you can say B has a unique relation to A. B has a direction. B has a path from there is a path from A to B, but not from B to A. You cannot go from B to A, but you can go from A to B. There is a direction, right? And this is represented by this arrow, by this ray, right? So this is a very basic thing. We most often we are asked to find the degree of a vertex. So what is the degree of a vertex? So number of edges coming or going of vertex, right? This is called a degree of vertex. So what is the degree of this vertex? Number of edges coming or going up this vertex. This degree of this vertex is 2, right? So similarly, total degree of a graph would be 2 into edges. So total degree of any graph will be 2 into the edges. Number of edges that graph has, right? Okay, so in directed graph, so in a directed graph, so right, I told you, right, a directed graph has a direction, one-way direction only, right? So in a directed graph, the degree might be different, right? So I'll tell you the example, but the in directed graph, the in degree of vertex, all the edges which are coming to that vertex, right? All the in degree, there's a in degree, there's a out degree. So in degree of a vertex is all the edges which are coming to that vertex. Out degree of a vertex is all the edges which are going out of that vertex, right? So that is the degree in case of directed graphs, right? Okay, so there is a path in graph, right? So I told you, like, there should be a path from one edge to another in a graph, right? So that path, we'll call it a path if that path contains unique nodes. There shouldn't be any repetition. No repetition. There shouldn't be any repetition. If that path has unique nodes, we'll call that a path. Okay, if that path has a unique node, we'll call that a path. We'll call that there is a path between A to B, right? If every node between A to B is unique, right? So there is a directed acyclic graph. Acyclic means that graph has a direction, but that graph doesn't have a cycle. This could be a graph, right? This could be a graph. This graph doesn't have a cycle, but this graph does have a direction. Does have a direction. This graph does have a direction, right? So there is also one type of graph which is weighted undirected graph. Undirected graph. Weighted means, I told you, these are the vertex. These can be anything. These can be named anything. A, 1, 2, 3, anything. And this, by default, in a normal graph, the weight of this, weight means the magnitude, you can say the value of this edge would be 1. But in certain cases, there is weighted graphs. Weighted graphs have different weights for their edges. The edge weight could be 2, 3, 4, anything, right? Ideally 1. Okay. Now, let's talk about now BFS. Now you know what a graph is. Now let's talk about BFS and DFS, right? So what is a breadth first search, or you can say breadth first traversal. Breadth first traversal. So let's draw a graph first, right? Let's draw undirected graph, which is A, B, C, D, and let's draw this E. So this is a graph, right? This is a graph, and this is a directed graph. This is a directed graph. So let's talk about breadth first search. Breadth first search or breadth first traversal is the traversal where we would traverse across breadth. Across breadth. Breadth means horizontally. Horizontally means in a more clear way, what I would say, if you are looking at a node, you should first traverse all the adjacent siblings of that node, or you can say you should traverse all the nodes adjacent to that nodes, all the neighbors. traverse all the neighbors first, then next. So you should traverse all the neighbors first, right? Okay, so we have this graph, right? We have this graph called A, B, C, D, E. So let's just try to find the breadth first, traversal first, then we'll talk about the algorithms, the type of data structure used to solve this problem, the code part, right? The implementation part of this algorithm, BFS, breadth first search, right? Let's just try to find the answer, the BFS of this graph. The BFS of this graph would be, let's say this is we start from A. We can start from anywhere, right? We can start from any node, any vertex, right? Let's just start from A. So we have A, right? Now this is a directed graph, right? We have to first traverse all the neighbors of A, right? All the neighbors of A, which is neighbor is B, neighbor is D. Okay, now let's just say we have now B. Okay, now we have to traverse all the neighbors of B. So A is already traversed, right? You see, and there is only one neighbor left of B, which is C, right? Now we should traverse the neighbors of D. D has only one neighbor, which is C, which is already traversed, and D doesn't have neighbor as A because it is a directed graph. There is only one path from A to D, right? So D has only one neighbor, which is called C, right? Now, and A and C are already traversed, so we don't need to do anything. Now let's talk about C. So C doesn't have any neighbors. Yeah, it does have. It does have neighbors, right? Does C have any neighbors? Yeah, C has one neighbor, which is E. Okay, C has one neighbor, which is E. Okay, and we can print that. Okay, now let's talk about E. E doesn't have any neighbor. So the traversal, you see A, B, D, C, E. This is the traversal, right? And yeah, your traversal could be different, but just remember, just make sure you follow this principle. You have to traverse all the neighbors first, then you have to traverse the other nodes, right? Now let's just talk about the implementation part. So BFS technique is solved by stack data structure. Is it? No, it is not. BFS technique is solved by queue data structure. Why? Right? So what we are doing here, right? What we are doing here. I'll tell you. Let me draw that graph AB of the BFS. So let's draw that graph again. A, B, C, D, E. You can add any relations. Okay, now BFS is solved using queue data structure. Why queue? Let's say a queue is a line, right? You make a queue doing anything, right? So always imagine the queue in this way, in a straight line, right? Queue in a straight line. So what happens in a queue? What happens not in a coding perspective, but as in general, what happens in a queue? People come from back and go from front. Whoever comes from back and whoever is the first, whoever came first will leave first, right? Whoever came first will leave first. This is a simple fundamental of a queue. Not in a data structure context, in a real world context also, this is a simple fundamental of a queue. Whoever comes first will leave first. People who came last, who are at the back, will leave last, right? So this is queue, first in, first out, right? So I'll tell you why we use queue, because let's try to solve this graph implementation using queue. So we have a visited array, right? Remember what we were doing in the earlier example, right? We were saying this is already traversed, this is already visited. So how do we know that? We have to maintain a visited array. So let's talk about the implementation of BFS technique, right? Breadth first traversal or breadth first search technique using queue data structure. We use a queue data structure while solving the BFS techniques, so, right? So what is a queue? So, in a real world scenario, not from the coding perspective, forget about that for a moment. So think about in a real world scenario, what a queue is. You come from behind, you go from front. In other words, whoever comes first will leave first, right? If you are at last, if you are standing at last in a queue, you will leave late, right? You will leave at the last, right? So this is the simple fundamental of a queue data structure. In coding also, what is it? It is first in, first out. Whoever comes first goes first, right? Now let's try printing the BFS of this graph using queue. So let's make a queue, which is a queue. Sorry about my line. Okay, this is better. Queue. Okay, this is the back, this is the front. Just remember like this. Okay, now let's start by this A. You can start from any element, I say, but let's just start by this element, right? So we have to print the BFS of this graph. We have to find the BFS of this graph. So whenever an element leaves this queue, right, will print that element, right? So whenever an element leaves this queue, we'll print that element. So that is what we do while finding the BFS of this graph, right? So we have to do this operation. We have to push the elements from the back, pop the elements from the front, right? So we have to keep doing this operation until the queue is empty, until we have traversed until we have traversed all the nodes of the graph, right? Let's start by A. Let's pop the A and print that A, and neighbors. What are the neighbors of A? B is the neighbor of A. We pushed B from the back. B is the neighbor of A, right? Now let's pop B, which is this. And what are the neighbors of B? What are the neighbors of B? There are no neighbors of B, right? There are no neighbors of B. If you see, there are no neighbors of B. There isn't a path from B, right? There are no neighbors of B. Now let's leave B. We can move to other elements, right? We can move to C, of course. Let's talk about C, right? Okay. Now we have C. We have an element called C. So let's pop C. What are the neighbors of C? A and D. So A is already traversed. We know that. We have to push D, right? Okay. Now let's pop D, and now we have to push the neighbors of D, which is B and E, right? But B is already traversed, so neighbor is E, right? So now we have to pop E, and we have to push neighbors of E. So E doesn't have any neighbors, so this queue is empty. And now our BFS of this graph is this: A, B, C, D, E. A, B, C, D, E. Simple, right? Now, so if you see, what we have done is, okay, if it is visible clearly, let's see what we have done is, so this is the breadth first search of our elements, right? So always try to create adjacency list. Okay, adjacency list is a way of representing graphs. So if you I like to implement, I like to represent, I like to convert my graphs first in this form, so that it is very easy to solve these graph problems because the relations are clearly defined. So why it is called an adjacency list? Adjacency list means every node of this graph will be a key and the relations will be defined as a list, as an array, right? There is a relation from, there is a path from A to B and A to C. So it is defined like this way. There is a path from B to D. It is defined in this. So remember, this is a directed graph, because if it wouldn't have been directed graph, there should be a path from B to A also. So, but you see, there isn't a path from B to A if there is a path from A to B. So it is a directed graph, right? So now what we are doing is, we have a graph, we have relations in the form of adjacency list, right? And now we are starting from a node A, right? So what we're doing is, so let's see, we are calling a breadth first print function which will print the BFS of our graph, which is this. So now if you see our graph, which is this is our graph. Okay, now this graph is taking an input of graph and source. Source is the node from which we are starting from, right? Source is the node from which we are starting from, right? Now I told you, right, we have to start from an element A, which is in the queue. So our queue contains an initial element, which is source, right? And I also told you we have to keep doing this operation until our queue is not empty, right? Whenever the queue is empty, we stop doing it. We stop doing everything. So we put a check while our queue is not empty, while queue dot length is greater than 0. We just pop the first element of our queue, right? Why we are doing queue dot shift? If you remember, what shift does is it removes the first element from an array and returns it, right? And this is what we need. It is a queue. Whoever, it is first in first out data structure. Whoever comes first will leave first. So whoever is standing in front of the queue will leave first, right? So we have to remove items from the front of the queue, and we have our current element. So whenever we remove something, we have to traverse its neighbors, right? We have to traverse its neighbors, and our neighbor relation is defined in this way. So this is our element that we removed from the queue, and we have to traverse its neighbors, and we have to push its neighbors to the queue, right? Push its neighbors to the queue, and we have to keep doing it again while our queue is not empty, right? So we are again doing it, right? We are again doing it. See, we are again pushing, we are again popping the elements from the queue from the front, and we are again and again doing until our queue is empty. So let's see what the result is. So our result should be probably, we're starting from A, right? So you can see our result came to be A, B, C, D, E, F, right? So if you put an extra F, the result would be this. So this is our result, what we got, A, B, C, D, E, F. Why? So this could be the graph. If you see, there is a relation from A to B to C, right? Let me draw that graph here, what I coded in there. So if you draw A, there is a relation B and C, right? Directed relation. The relation from B to D, there is a path from B to D. There is a path from C to E. There is a path from D to F. There isn't any path from E to F, right? Okay, there aren't any relation Okay, C is not connected. C is connected to A, C is connected to E, right? Okay, now if we try to find the path, the BFS would come to be A, the neighbors be C, okay, the neighbors of B would be D, right? Okay, the neighbors of C would be E, and F doesn't have any neighbors, right? This is our BFS. Okay, cool. So thank you so much for watching. In the next video, we'll learn about the DFS technique and its implementation and visualization in terms of code and concept both, right? So stay tuned for the next video and keep watching, and please do subscribe and press the bell icon for future videos. And if you did like the content, so please do subscribe. Thank you so much. See you again.